Hello dear students. Today we will see about infrared spectrophotometry. So infrared spectrophotometry is completely based on the infrared radiations and how the particular molecules are going to behave when they are exposed to the infrared radiation, and how exactly they absorb the radiation, and what makes them to absorb this particular radiation, what kind of changes these molecules are going to have when the radiation is going to get absorbed. All these factors, aspects, and the use of these particular principles we are going to see in this particular method. So you can see in this particular picture, it's a uh, infrared radiation spectrophotometry. Here you can see, so this is in means nowadays people are using the advanced method of infrared radiation spectrophotometry, where they are called as FTIR, Fourier transform IR spectroscopy. So Fourier transform is one kind of higher mathematical modeling through which people are actually analyzing the data which is obtained through the detectors, and these particular data is going to be used in understanding as well as to get the spectral lines which can be further analyzed in order to get the molecular structure. So IR spectroscopy is a very important method, so widely used as one of the basic tool in organic chemistry, even and biological chemistry also. So IR spectroscopy is mainly concentrated about the energy of a molecule. So here, as we have already observed, so whenever an electron is going to whenever an energy is going to be interacting with a molecule, that causes changes within the electrons, where the visible and UV radiations cause about changes in electronic energy levels, whereas in case of IR radiations we see the changes in a vibrational and rotational energy levels. So here what exactly happens is that whenever IR radiation is going to get absorbed by the molecules, there will be transition at the vibrational energy level. So therefore people can also call this particular method as vibrational spectroscopy. IR mainly used for structural elucidation and to determine the functional groups of a molecule. You can see this is a IR which falls into the range of about 10 power minus 3 centimeter size of one, and that falls next to the visible radiation. Energy wise, it's going to have approximately about 1 kilocalories of energy. So ranges between 1 to 10 minus 2 kilocalories of energy, and it causes molecular vibrations, particularly the vibration energy level is going to get changed. So IR is going to fall into 0.8 micrometers, that is 800 nanometers, to 1000 micrometers, that is 1 millimeter. So IR is further divided into near IR, middle IR, and far IR. So near IR is the radiation which is going to be near to the visible radiation, so that falls between 0.8 to 2 micrometers. Middle IR is the next portion of the infrared radiation, which is about 2 to 15 micrometer. Far IR is 15 to 1000 micrometer. See, infrared radiation, as I am telling you, when we are going to divide, or when we obtain the spectra from a prism, the visible light is going to get divided into VIB-IR, where R is the red radiation. This infrared radiation falls below this R radiation. So appearance of this particular radiation, usually color wise it will be in reddish in color. So particularly this radiation also going to be given out, or means well, the source is going to be usually in the red hot bodies are going to give out this kind of radiations, in simple words I can say. So the most of analytical applications are this infrared radiations mainly falls into the middle IR region, so where the absorption of radiation is going to be seen by organic molecules commonly. So you can see this is the kind of vibrations which we observe. So the molecules are made up of atoms which are linked by the chemical bonds. So in a molecule, when a radiation is going to get absorbed, we can see different kinds of variations with respect to the chemical bonds which is there in the molecules. So it can undergo like vibrations. You can see as this is a stretching vibration which I am actually showing here. So this is one kind of vibration which is going to be shown, and generally a molecule at its ground state itself, it's going to have some kind of natural frequency of vibrations. That means a molecule, when we say these molecules have these bonds, and these bonds are going to have some kind of vibrations which is shown naturally at the ground state of a molecule. So this particular vibration is going to get altered whenever an extra energy is going to be given into the molecule. So this extra energy in terms of IR, when it falls, so it causes applied it increases the natural frequency of vibration, or changes the natural frequency of vibration, gives out to an applied IR frequency of vibrations. So this particular applied IR means absorption of radiation takes place, and a peak is observed. That is nothing but, so the difference with respect to the vibration which observed. So different functional groups absorbs the radiations at a particular frequency and gives a characteristic peak values. So IR spectra of a particular chemical substance is also called as fingerprint of that particular molecule, because this absorption is going to be very specific with respect to the kind of functional groups and bonds that particular molecule is going to be possessing. So criteria for a compound to absorb IR radiation. So we come across with two main criteria. One is correct wavelength of radiation and change in the dipole moment. Correct wavelength of radiation is nothing but when a molecule absorbs IR radiation, the natural frequency of vibration of a molecule is going to same as the incident radiation. Means, so the natural frequency of vibration which a molecule is going to be possessing should be of the same kind of frequency with which that radiation is going to be get absorbed. So then we come across a change in dipole moment. Change in dipole moment is when a molecule is going to absorb the radiation, so that causes a change in the electrical dipole. So as we know, many of our naturally occurring organic molecules are most of these organic molecules, they are going to have a dipolic in nature because of the presence of different kind of atoms of different elements having electronegative, electropositive nature of this particular one, and because of that there will be a change in the means the molecule is going to have naturally a dipole existence, and sometimes dipole is also going to get established when the light means when the radiation is going to get absorbed by the molecule. So this is going to the means this alteration is in the electrical dipole is going to be seen. So where slight positive and negative charge are going to be get created on the atoms within the molecule. So molecular vibrations wise, we have two types of vibrations: stretching vibration and bending vibration. Stretching vibration, further it is oscillation along the line of the bond, means within the same angle or in the same kind of what you call symmetry, and the bond is going to get stretched. So it's either going to be get extended, or it's going to get the bond length is going to get extended, or bond length is going to get decreased. So this extension and decrease of bond length is nothing but the stretching vibration. So it occurs at a very high frequency of 4000 to 1250 per centimeter is the frequency at which the changes happens. The two types of change stretching we see: symmetrical and asymmetrical. Symmetrical is when both the bonds are going to get vibrated at the same time, so they are going to get stretched together and they get means get compressed together. So this is called symmetrical vibrations or symmetrical stretching. So there is asymmetrical vibrations, whereas one is going to get extended, stretched, and the other bond is going to get compressed. So the length of a variation of in the bond length is going to happen, so where one is going to increase, other is going to get decreased. So this is a asymmetrical stretching which we are going to observe. So this both kind of stretching is going to be observed in a molecule. So then we come across with bending vibrations. Bending vibrations, there are again, so here vibrations or oscillations which are going to go out of the plane. So here it's not going to in the same plane, so it goes in the out of the plane, is going to happen in bending stretch vibrations. It occurs at a low frequency of means lower energy of 1400 to 666 per centimeter frequency. And when you see the bending vibrations, there are two types. One is plane bending, in plane and out of plane. In plane we come across scissoring and rocking, whereas out of plane we come across wagging and twisting. So this is scissoring. So in plane, where in the same plane, so like scissors, we in the scissors how it's going to move, in the same way there is going to be movement. So that's why called as scissoring. Both the bonds move towards each other at the same time, they move away from each other at the same time. So bond angle is going to get increase and decrease here. Then in plane it is. Then another one is rocking. Rocking is the movement of bonds which going to takes place in the same directions. So like instead of going opposite, they go on the same side. So thereby they are going to show kind of rotational kind of movement, you can say. It's called rocking. Then we come across with out of plane bending. So out of plane bending, here wagging and twisting is there. Out of plane means here what happens is that in case of wagging, so one of the bond comes above the means moves one side of the plane, and other is going to move uh, up and down of the plane. That's called wagging. You can see here, there the movement is being shown. And there's one more kind of twisting. So there is like one atom moves above the plane, the other is going to move down the plane, that is called twisting. So wagging is going to be means you need to little more have a vision over there. So in wagging, both the bonds, they are going to move above to the side of the plane, like above they can move down, and below also they can go, that is simultaneously. In twisting, they are not going to happen simultaneously, so they move in opposite direction. So one, if it is coming above, the other one is going to go down. Then we'll move into the instrumentation part of the IR spectroscopy. So this till now whatever we saw, it's part of principle of the IR spectroscopy, what kind of alterations which happens in the molecule. So in the instrumentation part, so again it's very simple. It's going to have a source. In a very simple way, you can say source, monochromator, then there will be a sample holder followed by the detector, then amplifier. So this is what the simple one. And here since it's an IR spectroscopy, there is like you can do it simultaneously. We can pass the radiation through sample and reference. We can pass it one after the other also, for which people use different kind of mirrors. So there is a graters are also going to be used. So here very important thing in IR spectroscopy is, so commonly in IR we don't use the monochromator before the sample, that is between the source and the sample. We don't use monochromator. Instead we use a monochromator after the light or the radiation, sorry, not light, the radiation. After IR radiation passes through the sample, we are going to use a graters or monochromators are going to be used. Okay, so the type of source which are going to be used here, generally the source is going to be ideal source is a block body radiation, as I told you, or commonly used are going to be Glober filament or nursed Glovers. Glovers are going to be having resistant rods of silicon carbide, whereas nursed Glovers are going to have a spindle of rare earth material, means rare earth elemental oxides. So generally thorium and zirconium are being used. Globers, they are going to be generally give a longer wavelengths, and whereas nursed globers, they give shorter wavelengths of IR radiations. So for optics, that is the lenses which are being used are here mainly people use a number of mirrors. So these mirrors are being used in order to focus the particular radiation exactly into the sample reference as well as through the detectors. So there is M1 M2 which divides the beam, that is the source light. Then other alternative mirrors, they are going to allow the means the radiations to pass through the sample as well as a reference. Then later another mirrors are there, it simultaneously focuses the radiations onto the detectors, sorry, to the monochromators. Monochromators, here we use split the means we use mainly to get to particular wavelength of radiation. So here it's in opposite way. So in order to study the particular wavelength of radiation, we use a monochromator. So people use prisms, graters, and even both are being used. So resolution mainly depends upon the slit width and quality of the mirrors which are being used in the spectroscopy. So rock salt prism is generally used with a range of 650 to 4000 per centimeter frequency. Then there is detectors which are being widely used here. The detectors which to measure the radiations, particularly heating effect based one are used. Thermopiles, bolometer or Gole cells are generally used. Photoconductivity meters are also being used. Radiations are allowed to fall on the photoconducting material, and conductivity is going to be measured there. And once the sample absorbs the radiation, so then automatically there will be change in the amount of electrons released and as well as the current which is being generated. Then followed by that, there recorders are going to be there, which is going to also partially also amplification of signals. They are going to be moved on an alternator, and which cuts down the radiation among out of the reference beam until energy balance is going to be get restored. Then for this they use a motor which drives the comb into the reference beam first, and when an absorbing band is encountered, and out of the beam when the band is going to get passed over. So out of the beam absorbing, both are going to be studied, and the recorder pen is also coupled to its motor, so that as and when there is going to be changes in the absorption, so based on that there will be means graph is going to get created. So that is a part of instrumentation. So then we will get into the applications of IR spectroscopy, the usages. So I think it will be better if I take it together all in the next slides. So go through this particular principle as well as instrumentation. So it's a very important method, so please concentrate and understand, try to understand the process. In case of any doubt, please feel free to message or call. Thank you.